Okay, in this chapter we're going to talk about some very useful notation called sigma notation. And here's an example down here. You have the big sigma, this symbol here. You have the starting value, 1, the finishing value, 10, and the expression that's evaluated for each value of I. So how do we evaluate this expression? Well, it's going to have 10 terms, one with I equals 1, one with I equals 2, etc., all the way up to I equals 10. First term, when I equals 1, I get 1 plus 2 equals 3. Here's the first term here. I add that to the second term, which I obtain by plugging I equals 2 into this expression. 2 plus 2 is 4, second term is here. Then I plug in I equals 3. You see where I'm going from 1, 2, 3, all the way up to 10. I equals 3, I get 5. And you can see that if I continue this pattern with 10 terms altogether, so we got a small mistake here. No, we don't have a small mistake, I'm sorry. If you count there's 10 terms, the last term is going to be 12. If you sum these up, it happens to be 75. Now, you can sum it up the long way. We'll see later that there's a faster way to sum these things up. You may know the trick about how to sum these up. You sum the first and the last, and the second to last, and so on. But let me not talk about that trick now. Let's focus on the notation. Now, here's a sum that you might get a little tripped up on. The sum from I equals 1 to 10 of 5. Now, the result is not 5. This is an expression that involves the variable I. I is called the index variable. It just so happens that this expression is 5, and there's no I that appears. The summation still has 10 terms. Each term is 5. So that's how you get this result. 5. 10 terms means 5 times 10 or 50. It's possible for the index to be an exponent. So in this case, you'd have I equals 1 gives me 2 to the 1. Second term, I equals 2 gives me 2 squared, and so on. Again, we'll see later how to evaluate these sums. Sometimes a sum can have an unknown in it. So this x is an unknown variable. When you write out the sum term by term, the result will also have unknown variables. All right? So this is actually a polynomial. You can write any polynomial in summation notation. Okay. Now, if you do write a polynomial, usually in high school when you talk about quadratic equations, you talk about a quadratic expression. Quadratic polynomial is ax squared plus bx plus c. Now, if you do that, the summation notation is really not very useful because the first term has a c, second term has a b, third term has an a. And so the letters changing for each term. We don't have a regular pattern like we have up here. If instead we denote our coefficients in a more systematic way, instead of c we use a0, instead of b we use a1, instead of a we use a2. Notice the pattern here. I could write this a0 as a0 times x to the 0, a1 times x to the 1, a2 times x to the 2. You can see the regular pattern of these terms has the form ai x to the I. And in fact, we can use that expression in our summation expression. Notice here we're starting I equals 0. You don't have to start at I equals 1. You just start at some value and go up to a final value. It's understood that the increment is 1. So I should go up by 1 each time. So if I take I equals 0, then I get a0 x to the 0, which is this last term. I equals 1, a1 x to the 1, second term. I2 equals a2 x squared gives me the third term. Okay, so that gives me the equivalence between this and this expression here. Throw away some of the garbage. Okay. All right, now there's not just one way to write a sum. For instance, I have this, the sum of the first 10 integers from 1 to 10. Now, if I just wanted the last six, I guess it's the last seven terms, I could start at 4. Or if I just wanted to take the 3 terms in the middle, I get 4 plus 5 plus 6. Okay, so there's a lot of flexibility in summation notation. Okay, these are all sums that you should be able to evaluate explicitly. There aren't so many terms. Well, this one takes a little while. This last one down here, it's got 8 terms. So let's look at some properties of this notation. Now, consider this sum. Sum from I equals 0 to 5 of 2i. Notice you multiply each term in the sum by 2. Now, why not take the 2 out, take the sum from 0 to 5 of I, and then multiply by 2. This is a much more efficient way. You can always take a common constant out of a sum. This is the general rule. Right, but here we see why it works. Here are some other rules of sums. These are generalizations of rules you've seen in high school. If you take a sum of the sum of 2 terms, I can break up the sum in a different way. I can sum all of the x's and all the y's separately and then add them together. Doesn't matter which order I add. This rule combines the previous 2. This is what we would call a linear combination. So a linear combination of terms can be expressed as a linear combination of sums. Now, we can also change the starting and final value. If you think about writing this sum out from I equals 2 to 7, I minus 1, really the terms start at 1, 2, 3, 4, 5, 6. That's the same thing as just if I start at 1, go up to 6, and multiply by I. What's the difference between here? I really changed I minus 1 into a new I. All right. So I change this I minus 1 to I here. Then this I equals 2, if I change that to I have to change it to 2 minus 1 or 1. This 7, according to this rule, 7 minus 1 gives me 6. I change it to 6. And you can verify that these 2 sums give the same result. Okay. So here we have a similar example, a sum with 1, 2, 3 terms, starting from I equals 2 up to 4. Now, if I replaced I plus 1 with j, then what do I get? Well, this term is j. Then I plus 2 is I plus 1 plus 1. So this is j plus 1. I equals 2 here, but I plus 1 goes to j, so that means j equals 3. I equals 4 at the top. 4 plus 1 goes to 5. So this is an equivalent expression using a different index variable. So this is an alternative explanation of what I just said. All right, now, sometimes you want to split the sum up. In particular, sometimes you want to separate off the first term or the last term. Now, here's an example where we separated off the first term from a summation. Here's my summation from 1 to 10, I. If I separate off the first term, I get a 1. That's when I equals 1. The remainder of the indices run from 2 to 10. Now let's have some fun and do some manipulation. Suppose we replace the I minus 1 with I. Now that's the same thing as saying I goes to I plus 1. Okay, so that means I replace this I with I plus 1. Now, I minus 1 goes to I, so what does I minus 1 start at? I minus 1 starts at 1 and goes up to 9. So these two terms here are equivalent to these two terms here. Now we know that if you have a summation of with two terms inside the sum, you can split the sum up into two parts. So here you have a 1 plus this sum plus a sum of 9. Now this sum of 9 is just 9. The 9 adds to 1 gives me 10. And you can see what you have here is the summation with the last term split off. And I didn't have to do all this fancy stuff in the middle. I could know right away that I can express this summation, I equals 1/10 of I, as the first 9 terms plus the last term. By the way, it's especially useful to split off the last term when you're doing induction, as you can see if you go to the induction chapter. Now, this is not the only way you can split up a sum. You can split up the sum into multiple parts. In this example, we took this summation, took the first 3 terms here, 4th term, and the last 6 terms here. Okay, so here's some exercises where you change around the indices and make them work. Okay, another example. Okay, let's stop here.